Okay, at this point, we're going to start to transition into applying this to chemical systems. In this case, it's useful to have some sort of big overall summary equations. We've done these gas processes, but some key sort of equations that we're going to keep using over and over going forward. First, constant volume is a very convenient way to determine delta U. At constant volume, if we go in and use the differential form of the first law, we have du is d bar q plus d bar work mechanical. I'm going to just arbitrarily say there's no, well, let's leave the non-mechanical work in for now. Okay, so that's our at constant volume equation. Remember that since d bar work mechanical is negative p external dv, at constant volume, there's no dv. And so since that's 0, we have the mechanical work is 0. And we can completely eliminate that term. So at constant volume, we have du is d bar q plus d bar work non-mechanical. If I integrate both sides here, I get delta u is q plus work non-mechanical. Okay, this is really useful now because in normal chemistry, we're not going to do any non-mechanical work, and so the heat flow that we measure directly tells us delta U at constant volume. Or similarly, if we use adiabatic walls, then the work that we do directly determines delta U, which we could measure with, say, our resistor system, like we've done in those examples. Okay, but again, most chemistry and biology occurs at constant pressure, where there is always some amount of mechanical work, which at constant pressure is negative the pressure times the change in volume. So we always have this mechanical work term that's going to be a factor at constant pressure. So again, in thermodynamics, we can define variables however we want to make our lives easier. Again, maybe it doesn't seem like it's easier, but it is easier than the alternative of directly accounting for this every single time. So we're going to define a variable enthalpy H, which is U plus pressure times volume. So the idea here is now to use our derivatives and everything like that, use the differential form of the first law and all that kind of stuff to derive an equation analogous to number 1 here for delta H at constant pressure. Okay, what that looks like then here, the idea here is H is equal to U plus PV. Now, what we're going to do is we're going to take the derivative, or the total, take the different. So we're going to do sort of the differential here. So we can say dH is du plus, for PV, we need the product rule. This is PdV plus VdP. Okay, and now let's use our given information here. So VdP, we're at constant pressure. So dP is 0. So this term goes to 0. And that's using the fact that we're at constant pressure. Now du, we know what du is from the first law. That's d bar q plus d bar work mechanical plus d bar work non-mechanical. So a little bit to write out here, but not too much. D bar q plus d bar work mechanical plus d bar work non-mechanical. Plus we still have a PdV. Okay, now just one more step here and everything will sort of simplify to give us the analogous equation here. So dH is equal to d bar q plus the mechanical work is minus p dV. Okay, the steps here. This was negative p external dV But again, since we're at constant pressure, so constant pressure means that the pressure inside our system has to be equal to the external applied pressure throughout the process. So P external is equal to P. So we get a minus PdV. And then writing out the rest of the terms, d bar work non-mechanical plus PdV. And now what's happened here, the reason enthalpy was useful for us to define was this minus PdV, and plus PdV terms are going to cancel exactly. And we're going to get a final answer here, which is dH is equal to d bar Q plus d bar work non-mechanical. This is going to be true at constant pressure. And again, we can write this in the integrated form, integrate both sides, and get delta H is Q plus work non-mechanical. And again, I'll include the caveat there, constant pressure. Okay, so this analogy really works quite well. At constant volume, delta U is equal to Q plus work non-mechanical. So we can sort of easily figure out changes in energy by either measuring the flow of heat or by doing some work on our system. We can do the exact same thing at constant pressure by switching from energy to enthalpy. So we'll show how that works then in terms of heat capacities next. Okay, so here is sort of another definition of heat capacity. We'll show that it actually matches the definition we had before. But the reason it's called heat capacity is that it's going to be the heat that flows under a specific situation. So CV, we'll say, is equal to, defined by this equation, it's the differential flow of heat is equal to CV times the differential change in temperature under a condition where there's no non-mechanical work, and of course it's CV, so also we're assuming constant volume. Right, so if we're at constant volume and there's no non-mechanical work, the flow of heat is given by the heat capacity times dt. And let's see what that actually gives us in terms of the change in energy under this situation. So we have our equation from before, du is d bar q plus d bar work non-mechanical. Okay, well, we've just defined that the non-mechanical work is 0. So under this situation, du is equal to d bar q. And so therefore we can say that du is equal to CV dt. And sort of moreover here, if we want to get a change in u, we can integrate this. Delta u is equal to integral of CV dt from ti to tf. And now, since there's no more bars here, right, this is always true if we do a process under the given condition. So if we're at constant volume and we change the temperature, we can always get the change in internal energy by using the constant volume heat capacity. This does match our previous definition as well. Remember that the formal thermodynamic definition is du dt at constant V and N is equal to CV. And we can see that this matches this definition here because we have du is equal to CV dt. And so du over dt is equal to CV. Again, our conditions here were constant volume, also constant moles. We're not changing moles in any of these processes. And again, the no non-mechanical work, that's not a limitation here anymore because this is our definition of heat capacity, but we're just basically verifying that this other definition works as well. So yeah, this works here just as well. Delta U is always this integral, and then this is Q is equal to this. When we're at constant volume, and again, the star, no non-mechanical work. So the heat capacities are really useful. If we're changing temperature, we can easily, at constant volume, we can use the heat capacity to get delta U. In the exact same way, if we use this definition of Cp in terms of the heat as the amount of heat at constant pressure with no non-mechanical work, we get the exact same result. dH is d bar Q plus d bar work non-mechanical. We're setting non-mechanical work equal to 0. And so dH is equal to Cp dt. And now if we integrate, delta H is equal to Cp dt from our initial to final. Right, this is going to be true at constant pressure. And I guess maybe technically also constant moles, but we're not really changing moles here. So this is describes how we can easily measure changes in enthalpy by using the heat capacity. Again, just like we had before, Q is equal to Cp dt Ti to Tf, and that's going to be true at constant P and N, star with no non-mechanical work. So, yeah, both of these definitions work, and this does agree with our previous definition that the heat capacity was dH over dt, constant P and N, right? We always need to get our definitions into this format because this is now in terms of real thermodynamic variables. But this does sort of show that it's called the heat capacity because it tells us the flow of heat under these common situations. So anytime we're at constant pressure with no non-mechanical work, we can easily get the heat by just using the constant pressure heat capacity. And similarly, even if there is mechanical work, we can always calculate delta H directly from the heat capacity because delta H is that thermodynamic variable. So it doesn't matter how we go from initial to final. If the pressure is constant, this is delta H.